Okay, so we were looking into swing limits, and we saw an example of the swing limits. And why was this swing limits and all those things important? It was kind of important because we wanted we not only want to use small signal model, but we at the back of our head we understand that these incremental small signal models are a smaller picture of a bigger. It's only a small contraction of a bigger picture, right? Which includes MOSFETs. So now when you have MOSFETs, we know that MOSFETs cannot operate in all regions of operation, which means you'll have to ensure that the regions of operations of the MOSFETs are where you want, which in our case is on and in saturation. So with that perspective in mind, we were delving into swing limits from the idea that ultimately this will be an amplifier, and amplifier will have large gains, which means it can have a large output swing for a given input swing, which by the definition means that if there is a large, there will be certain MOSFETs which will tend to go out of its safe region of operation and go into either cutoff or in triode, right? So so with that in perspective, we started delving into swing limits. But at the back of your mind, you should always keep in mind that all these things are happening because we are trying to get a large gain amplifier. Okay. So if you don't have gain, there is no swing, everybody is happy, but there's no point in making a feedback circuit then. Okay. So now let me take you back to one of the one of the circuits that we discussed, I think 6 lectures back or 7 lectures back. So the issue, one of the issues with this common source amplifier that we were discussing so far, one of the issues of this is that we saw that we cannot get too much of gain. One of the reasons is if I try to increase RL with a finite voltage supply, the transistor goes out of saturation. So, but I can then say that why use RL, get rid of RL? I'll use a current source to bias. I can do that, right? So I take a current source, ID or I0, let's say, and I bias my circuit, and let's say this is VG. So now tell me, will this work? No. It will not work. Why? Two independent sources trying to set the same thing, and they are not talking to each other. So what was the solution we came up with? And forget about the biasing, incremental input for now. So what was the solution? We connected gate to drain, right? So essentially, what were we saying? We were saying that we'll be looking at the drain input, drain voltage, and take a call how to adjust the gate voltage, right? And we said that, and we saw that a simple connection between gate and drain or drain and gate suffices. Okay, so this is a very well-known circuit, direct connected circuit that we are familiar with. But I mean, from this very argument, you can come up with multiple configurations, and it is based on the fact that you have to come. If I want to bias a circuit with a constant current source, which means I have to add a current source either at the drain or at the source, right? I cannot add it anywhere. So these are the places I can connect my current sources. But how can I change the operation of the MOSFET from the input side? I can change it by affecting the gate or affecting the source, right? So these are the two independent terminals, control terminals that I can tweak. Or in other words, what I am saying is that if you have to bias your transistor using a current source, using negative feedback, right? This example was that of a negative feedback. We were observing the voltage at the drain, and we said that if the drain has increased, drain voltage has increased, which means that we are concluding that the strength of this MOSFET is do I need to increase or decrease the gate voltage? Okay, maybe I have lost you. So let's assume that you are sitting in the lab, you have connected your circuit like this, and you have applied a variable gate voltage here, and you observe that this voltage has increased. I mean, beyond some reason, this voltage is increasing. If the voltage is increasing, what is the conclusion with respect to, let's say, the current that is being sucked in by? So, which means that your IDS is not high enough, right? So your I0 is a constant current source, and this common voltage, this voltage that I have marked here, the drain of the transistor is increasing, which essentially means that your IDS is lower than I0. That's why it is increasing. Which means that if I have to balance everything, I have to increase IDS, which means I have to increase VG, right? So essentially what we did was we essentially in our mind, we applied negative feedback and you connected it like this. Now that you know what loop gain and all those things are, you can as well say that I will break the loop here, apply a test voltage here, and observe it here. And you know what the loop gain will be. It will be GM of this transistor times whatever output impedance you have, whatever GDS you have. That's what the loop gain is. But this is the point that I am trying to drive home here, is that this is not the only way to bias your transistor using constant current source, because we have many terminals. Right? Rather, I would say that I can observe this is the case where I observed the drain and applied some action at the gate. Right? So this is the case where I have observed the drain and I had feedback action at gate. Okay. So now I have options of observing the drain and applying a feedback at source also, in principle. Similarly, I can observe at source and apply feedback at gate. Or I can observe at source and apply feedback at source itself, because source is both controlling and control terminal. Right? In principle, I can do all four. And obviously, I cannot apply the feedback at drain because that is not a controlling terminal. The drain voltage is not controlling the current of your MOSFET. I mean, you might say there is a GDS, but that is a very weak control, right? So you don't get too much of control from GDS. Okay. So now let's continue with this case. Let's continue with this case. So this will bias your transistor as you want. But one of the reasons we wanted to bias the transistor with a constant current source was, in this case, the fact that we wanted larger gain. Right? We wanted to get rid of that RL that was there in the common source amplifier, and we replace this. But now, which means that I plan to apply an input Vi and take the output from this terminal, right? So ultimately, I have to connect it up in such a way that I still get the gain, maximum gain that I aspire to. Okay. So now tell me, how should I go about connecting it? Because ultimately, see, what is the small signal picture that I am looking at for this amplifier? The small signal picture or the incremental picture that I am looking at is your Vi should appear here, and this current should be GM times Vi incrementally. So this is the picture that I am looking for. But I have this transistor which is biased with the constant current source like this. So how can I superimpose this incremental picture onto this transistor picture or the biasing picture, right? So this is how I have biased it up, but now I have to apply a voltage source and incremental voltage source and take the output. Ideas? No, let's not tamper with the source as of now. Let the source be as is. There were some questions. Yeah. Correct. We are looking for coupling those two. Okay, so we can couple the capacitor, but I mean, what he's essentially saying is, as long as we are not particularly bothered about the fact that Vi is a DC, right? So I can use a capacitor to couple. So now so now will it work? Vi is sinusoid. Okay. So now will this work?
But there is no gain.
Yeah. So then will it work? Then what do you mean by it will work? Well, the bias condition is not getting hampered, but I mean, incrementally, when you are doing an incremental analysis, you assume that this capacitance should be very high, right? It's shorted for signal frequencies. That's what the assumption was. So if it's shorted for signal frequencies, what is the incremental picture? Well, there are many ways to do that. Let's not tamper with the source now. We'll tamper with the source in another example. So let's say this is VG. So now this is V0 also. VG and V0 are connected, right? So this is GMV VG. This is RS. So clearly, this is a V0 is a voltage divider between RS and GM, 1 over GM, right? So you will not get gain, you will get attenuation, right? So by the way, I mean, just out of curiosity, what will be V0 by Vi in this configuration? Exact expression? Fine. So, so this is not clearly, it's not working. So what should I do? Add a? We want a buffer. We want to design a buffer. Where do you want an inductor? Okay. He wants to add an inductor here. Okay. What purpose will this serve? Will this serve? Yeah. So what I mean, if I assume this again, this L to be very high, right? So then does it work for our purposes? So at signal frequencies, you can assume impedance given by C is 0 and impedance given by L is infinity. Will DC operating point get shifted? At DC, what is the gate voltage? What is the impedance given by L? 0, right? And there is no current anyway in this. At DC, there is no current, right? So this IDC gate is 0, right? So at DC, your gate to source voltage is still, by the way, what is the gate to source voltage in terms of I0? What is VGS? Q? What is the expression? Yeah, and what is it? What is the expression? Threshold voltage plus under root of 2IT. Very useful expression. You should always keep this in your back pocket. Okay, fine. So your VG has been set up using this, and this clearly brings out the fact that if you want large I0, your VGS will be higher and so on. But at least it has to be threshold voltage or more. So now what under the incremental? If I do an incremental picture of this, what does it look like? You have Vi, you have RS, and then what? So this is the gate VG, This is Gm times Vg. And what is connected between here to there? It's an inductor, and the value of the inductor is infinity, right? That's what the assumption was. So this becomes an open source. So this clearly gives us the contraption that we want. Okay. But the problem is in IC, you can do it in discrete design, no problem. But the problem with IC design is that it's very difficult to make inductors on chip. Okay, so so unless we are operating at really high frequencies, few gigahertz or higher, right? So you don't really get inductances of appreciable values, right? Because your impedance of your inductance is omega times L. At low omega, naturally the impedance is lower. At high omega, your impedance is higher. And the value of L's that you get on chip is typically of the order of few nanohenries at max. You don't get more than that, which means you have to go at multi-gigahertz to get any appreciable value of inductances. So if you are operating on sub-gigahertz range, generally you will not see inductors being used. So if we cannot use an inductor, right? If we cannot use an inductor, what is the next best solution? So we cannot use an inductor. So the next thing is, can we just insert and check whether we can use a resistance or not? It might or might not, but unless you do the analysis, it's difficult to tell, right? So now what is the issue with, if at all, what is the issue? What issue might there be using a resistance? Not in this particular case, but anywhere instead of an inductor? It might be that it takes up some DC current and you have large drop across the resistor itself, right? But in this case, clearly this current is zero, right? Since this current is zero, you don't have any current through RG, which means there is no drop, which means the voltage at the drain and the quiescent voltage at the gate are identical, which means that we should be able to use this. Okay, does it make sense? So now, once we arrive at this topology, which might be acceptable, then obviously we have to look into the cases where under what values or what ranges of values of RG, C, RS, and all those things will this circuit work in the way that we want it to. Okay. So obviously, when you do the analysis, you say that RG is infinity, C is infinity, everything is infinity, but in real design, nothing is infinity. So you'll have to figure out the range, minimum range, maximum range, and so on. Which means we go back to our drawing boards, do our small signal analysis again, and then try to figure out what's happening. So let's do the small signal of this. So now, okay, so even if we do the small signal of this, let me ask you, what is, I mean, how do you even, let's try to figure out what is the constraint on RG first. Okay, so you can write out the full-blown equations and then get a couple of constants, one on C, one on RG, and then figure out what the math throws up. But is there any other way of approaching this problem? And what we circuit designers tend to do is to bifurcate our problems into multiple smaller problems and then try to deal with each smaller problems separately, right? So that helps our cause. And this is a general design principle across engineering, that you have a bigger problem, you break it up into smaller pieces, smaller manageable pieces, and attack each of them separately, divide and conquer, right? So the first thing that in this case we might want to say is that let's assume that we have achieved the condition of C equal to infinity, right? means that I'm applying at certain frequency ranges where C is not giving me adequate impedance, it's the short. Then I would like to figure out what is the constraint on RG. Okay. So let's assume this, if that is the case, what is the small signal equivalent circuit of this? This is RS, VI. And you can also add up the GDS here because your transistor actually has a GDS. You cannot really, or I can simply say RDS. Neglect it. At times you can, at times you cannot. But in this case, obviously we cannot neglect it because ultimately if we neglect GDS, we want a common source amplifier. If we neglect GDS, it becomes in your intrinsic gain of the amplifier becomes infinite, right? Which clearly is not true. So in those cases, we cannot neglect the GDS. Okay. Particularly if you are looking for gain, if you are trying to figure out what the gain is. So now, if this is the condition, what is the constraint on RG? How will you what will you do to figure it out? See, ultimately we want this, right? If I take you back to the class where we discussed about y parameters. Pardon? That's the hope, right? We want common source amplifier, right? But to figure out what is the constraint on RG, what is it that if I take you back to the two-port network diagram, right? We had, I think, second class or third class, I don't remember. We had this two-port network. This is one Y11. This was RS, VI. Then you had Y21, V1. Then you had Y22. And then you had RL. And I'm obviously you don't have Y12. I didn't put Y12, that's why. So this was V1. Okay. So what was the constraint on Y11? We wanted it to be 0, and why? We wanted the entire VI to appear at V1. We didn't want to have any drop. Which other way of saying is that Y11 to be 0 means that whatever is the stuff that you are looking in should have zero impedance, zero admittance or infinite impedance. Now, you obviously cannot have infinite, which means that you have to say that this impedance looking in has to be much greater than RS. Right? That is another definition of practical definition of infinite in our case. So, which essentially means that if I look at this terminal, this contraption, and say what is the input impedance here, this Rin has to be greater than RS. Okay. So, Rin has to be greater than RS. So, what is Rin of this contraption? I think this was one of the assignment problems also, right? What will be the input impedance of that contraption that is highlighted here?
RG plus 1/5 GS.
Yeah, so it's basically if you Rin is this resistance plus this resistance divided by 1 plus the gain, right? So this was RG plus RDS by 1 plus GMRDS. And if we assume GMRDS to be high because that's what we want, so this becomes approximately equal to RG by GMRDS plus 1 by GM, right? And this has to be much greater than RS, right? So from there you get a constraint on RG. Okay. So this is one constraint on RG. This is a constraint on RG that you get, assuming that the capacitor is perfectly shorted. And let's assume now, by the way, any questions before we move on? So this equation I just plucked out of memory, right? So you can solve, go back to one of the first assignment or second assignment, something like that. So if you figure out what is the input impedance, you will get that and essentially use it.
So we may also want that the GM, DC current, all of the current must flow through the RDS, not in the RG side as well.
Yeah, we would want that also, and that will get another constraint because of that. You'll get another constraint, right? So what he is pointing out is that this is only we looked at the input side, right? But also we had a constraint here, right? We also had a constraint on the output side, and the fact that whatever current that comes out of Y21 should flow into the load, whatever the load might be. It should not go anywhere else. So what he is pointing out is the current that flows out of here can go into RDS, also can go into RG. Right? Looks like there is a division. So from there you will get another constraint. But as it, I mean, we don't have time to do it this today. So I'll leave it to you to figure out the constraint on the output side. We'll discuss it in the next class. Okay, and you will see there is some interesting takeaway from there also. Okay, so now let's do the final one. That is, this is the constraint on RG. What is the constraint on the capacitor? How will you figure it out? How will you figure out the capacitance? Anyway, I mean, whenever you are trying to, this is the first order circuit. You have one capacitance and bunch of resistances, but effectively you can reduce it into a one capacitance and one equivalent resistance.
So what is it? GM RS RDS minus RDS. GM RS RDS minus.
Correct, right? Yeah, you are right. So, thank you. Something is wrong. What did I do here? Minus RDS only. Correct. Yes. Yeah. Thank you. So yeah. Thank you, because otherwise again next class I would have had to issue an errata. So in this, if you have a circuit of any circuit which has one capacitor and bunch of conductances wrapped around it, how do you figure out the constraint on the capacitor? You essentially say that I'll reduce it into a first order circuit, which is a capacitor and whatever R I see around it, right? In this case, RS, and what is R equivalent. And then I'll reduce it into a time constant, and then from there I'll get a constraint. So in this case, you already figured out what is R equivalent, right? This is R in, which was this RG. From where you got the constraint on the RG. This is not RG. The constraint on RG, that one of the constraints on RG that you got was from looking into the terminal of looking into the gate of this on the other side of the capacitance, which essentially means that the constraint on this capacitor will be in terms of R in, RS, Can you tell me? So constant on C for it to behave like a short circuit.
Time constant should be very, very small, like C into R in and plus RS.
Time constant should be very small or very large? C should be high, right? Right. So what is the time constant here? Tau is
C into RS
RS plus Rin into C, right? So with I mean, how does this tally with the frequency of the input that you are looking in? If you don't recall that, the other way of looking at it is that the impedance given by C has to be smaller than the resistances, the impedance offered by all the other resistances put together, right? So essentially, omega C or omega naught C, whichever frequency you are operating in, has to be much less than Rin plus RS. Sorry, 1 over this, right? This has to be greater than 1 by Rin plus RS, right? So which means C has to be much greater than 1 by omega naught Rin plus RS. Okay, so you can approach it from time constant perspective, you can approach it from impedance perspective, you essentially get the same answer. Okay. Okay, we'll stop here. Any questions?
Sir, how can we intuitively look at this constraint in this circuit, sir? If the time constant is very high, in that case, how this V and VGS is affected?
Okay, so if time constant is very high, which means C is effectively shorted, right?
C is shorted. Okay.
If C is shorted, then you already ensured that Rin is much greater than RS in the previous approximation, right? So if C is shorted, then anyway you are able to implement this voltage at Vg to be equal to Vin, right? If C is shorted, then it's not a problem. And this constant that the thing that we discussed right now is what is a constant to make C to be short.